Hi everyone, and welcome to the next video for this new session in the course. And the next set of videos will be focused on geospatial data, which is a kind of special form of data, but just because it's very common, and chances are that, like, if you work in this space, that at some point you'll encounter or you run into geospatial data, just because it's so linked to the real world. We decided to have one full session dedicated to it. And also because, at least personally speaking, I feel it's also quite a fun type of data to be working with. So first, we'll give a bit of an introduction in this video. And I'll start right off with the very basic question of what even is geospatial data. So what defines geospatial data is that it's data that is linked to real world locations on Earth. So, I mean, on this very planet we're on. And this is actually the case for a surprisingly large amount of real world data, at least. Like, once you start working with real world things, they're actually quite often also linked to some places on Earth somehow. And in general, the software that you use for working with this type of data is typically referred to as Geographic Information Systems, or in short, GIS. And the only reason we're saying this here is that this is a really good buzzword or abbreviation to keep in mind. When, for example, you search for anything in this space, GIS is usually the term used for anything, really. Next up, what makes geospatial data special? Like, why is it not just the same as any other form of data, right? Besides linkage to the real world. And to say it like very bluntly, because Earth is round, so that makes it a bit more complicated sometimes to work with geospatial data, just because of the coordinate system that we have to use for it. Because we can't just use like a normal Cartesian coordinate system, because we have to map it somehow to this ball or this round ellipsoid. But of course, not like a perfect sphere, sadly. And the way this is done is that typically, at least for coordinates, latitude and longitude are used. So latitude is kind of like roughly corresponds to the y-axis. So how high up, one might say, so on the north-south axis, where something might be located, in degrees north or south, as you can see here. And you already see that, like, we're using degrees here instead of something like, I don't know, yeah, just arbitrary numbers or something, or like kilometers or meters, just because this is the best or the easiest way to refer to places that are located on this round object. And then for the x-axis, there's longitude, which is given in degrees east or west usually. I don't know why there's an O here. Weird. But basically that's kind of, yeah, where you are on the x-axis. So for example, there might be a place that is on the same height. So for example, two places in North America and Europe, they might have the same latitude, so the same y-axis, because they're kind of both in the upper hemisphere. But then they would have very, very different longitude values, with one being much further east and one much further west. And you can also see here that for both the 0 degrees is close to the equator, on the latitude, and on the longitude, it's Greenwich, so it runs straight to the UK. It's kind of this arbitrary place, but maybe you've heard about it, because it also is used a lot when it comes to time. Yeah, and then one more minor detail that's related to this, because these coordinates are on this sphere, and they're in degrees and not like kilometers or something, you will have to take this into account when you calculate anything like distances, because, for example, and maybe you can already think about this, right? Like we've had, for example, here, we have 30 degrees here, and 60, 90. But so, for example, a change of 1 degree up here, close to the poles, actually means much less than a degree, in terms of distance, than a change of 1 degree close to the equator. So these coordinates are becoming a bit more rough closer to the equator, which is really actually quite an important thing to keep in mind. Because, for example, let's say you anonymize something by rounding these coordinates, then you actually have to take this into account. So rounding to the same number of digits means something very different in Europe than compared to Africa, which is close to the equator, of course. So this can really lead to like some very interesting things, that somehow affect any sort of calculation or something. And there's solutions for all of this. You can just search for it or use the correct package, but we just want to tell you that this is something to keep in mind. And to make it a bit more complicated, besides latitude and longitude, there's also different coordinate systems. And just to, again, give you basically the buzzwords here. So a very common one is EPSG 3587, which is used on the internet for many things. And then the other one is WGS 84, which is the same as EPSG 4326. Don't think too much about this, but that's actually the one used in GPS. So it's just like two different coordinate systems, and there's many more. Also, for example, like just for Germany, there would be one that's like very well suited for like doing anything in Germany. But again, this is something you can mainly ignore, and as long as you use the same coordinate system, everything just works. But again, just to like kind of give you this overview of these are the kind of things that you could run into that might make your life a bit harder. And yeah, again, just to say this again, like many of the normal calculations that we would do to, for example, calculate a distance, like a geometric distance, which you might remember from your math class, back even in high school, all of these expect Cartesian coordinate systems. And so you will always just have to take this into account. And again, you can just Google for the formulas for this. You don't need to like do all this by hand, but it is a thing, and that's why I want to like tell you about it. Okay, continuing on how this may affect things. So for example, if we just naively plot data, because we can just plot geospatial data even in ggplot, which is really nice, but then we might get this. So this is a map of Germany, and if I just plot this on a Cartesian coordinate system, we get the following. And we see it looks a bit off, right? Like it's a bit too wide for what we would expect of Germany. Some of the proportions are off. And that's because now we try to plot this in a normal coordinate system, but we actually need to use a geospatial one, which you can just do with a coordinate map, and we'll talk about this in class. But then you actually get like a properly sized Germany. And of course, with Germany, it's really obvious now, but with maybe if you're plotting just points or something, it can really be distracting or like confusing if something is off with these coordinate systems. So again, just something you always have to keep in mind. Usually the fix is very easy, but you will have to do it. And lastly, this goes a bit back to what we did here with Germany, but just on the bigger scale, because of course we have this sphere of the Earth, and whenever we try to map it somewhere, we need to project it, because of course all our screens are kind of 2D and usually rectangles. And then so somehow we have to take this sphere and then unroll it to put it on the on a flat surface. And this is exactly what a projection does. So what we do is we project this ellipsoid to a 2D surface, and you need to do this for maps, but also for any sort of visualization if you want to like highlight something. And the problem here is that there's not really one solution to this. There's one very like well-liked solution, but they all come with like their own kind of problems. And the most common one is Mercator, which is actually quite old. I'll talk a bit more about it later, just because it's like a very famous one. But there's also, for example, the Lambert conformal conic one, or like the geographic one, and many more. Just to show you that there's different options for this, and depending on which part of the Earth you want to focus, or which kind of region, different ones might be better, or what you try to show. Right? Like also if you, for example, focus on the oceans, you can see that maybe this one is more well suited than this one. And to talk a bit more about the Mercator projection, so just because it's so famous and so well known, it goes back to 1569 actually, so quite old, and was developed by Gerardus Mercator, and it's quite accurate near the equator, but then any areas that are further away from the equator are enlarged to kind of fill in the gaps, right? Because of course we have the sphere, and it's like also, if we just naively put it down, it's like the longest around the equator. So it just works around this, and the result of this is that some countries on the Mercator projection are like seem much bigger than they actually are. And the classic example for this is Greenland. So up here, which is actually like, it looks huge. It looks like the size of Africa here if you look at them next to each other, whereas in reality it's much smaller. And you can check out this website, thetruesize.com. I can very much recommend it. It's fun, and just to kind of show you how much these things are distorted. I think it's good to be aware of this, and of course, because it will also affect any sort of visualization that you do. That everything, the further you go from the equator, the more it is like kind of zoomed in, which of course, for example, is also the same case for Europe. So one of the weird things with this is that it always kind of, Mercator projections show Africa like significantly smaller than it actually is. And depending on what you compare it to, the effect is like very big, or like not too big. It really like, it just scales up. And with this website, you can just drag around things, and it's really fun and shows you the degree to which this affects certain countries. That's it for this video, and I shall see you in the next one. Here's briefly the sources for graphics and everything.